Okay, so whenever we analyze the antennas, we can have electric dipoles and magnetic dipoles. So the equations that we use for these, they are pretty much symmetric with respect to each other. And in fact, you might remember that from the courses that you have taken, starting from the electromagnetic field theory, always, especially, it is very it's very obvious when we derive from a small electric dipole, which is equal to QD. So we used to calculate the potential and the electric field of a dipole. Meanwhile, we had also another magnetic dipole, so the vector is in the area, and from here we used to calculate the potential and the electric field intensity. And these two expressions, they were pretty much equivalent with respect to each other, other than the fact wherever in these two expressions, if we had the P was substituted for the M. So this is the dipole moment. Okay, this used to be the dipole moment. This was the magnetization. What did we call this one? Magnetic moment, I think, a magnetic moment. So in all of these expressions for the potential and the electric field intensity, we can derive everything for this second configuration by substituting the P with the M and substituting the epsilon 0 with mu 0, and everything, it was all the same. So if the potential was changing as 1 over r squared for the electric dipole, the same way it was also changing for the magnetic dipole. Now, why do we mean this here is that in chapter 3 predominantly, and also we talked about this one in chapter 4, we saw that we have a duality, or there is a symmetry between the fields that we observe when we have an infinitesimally small electric dipole and infinitesimally small magnetic dipole. And then what we may say is that if for one configuration we obtain, let's say, ER, E theta, and E phi, immediately these expressions can be, so if this would be for the electric dipole, for the magnetic dipole, we would simply write HR, H theta, and H phi. So nothing would change. Well, not always nothing. There is a minus sign. Often we might get a minus sign. But the rest of the terms, they will be pretty much similar. So this means that if we have a configuration of an antenna which is emitting a specific radiation because of the electric dipole, we find the electric field and the magnetic field intensity. Meanwhile, we can just substitute the expressions one-to-one correspondence, and we still get the exact equations. Okay, so nothing will change. And regarding this, I might suggest you to go over slide 13 of our lecture notes. So please, if you have downloaded it, you can go to slide 13, and you can check also page of the book, page 138 and 148. So if you go to these pages, you're really you can, as I said before, you need to refer to these because you have the midterm next week, and these are essential elements that they might use. So let's assume for a moment that we have instead of, so we have an antenna. One second here. Here, let's do this example. We have infinitesimal small magnetic dipole. I don't know how we spell infinitesimal. Is it with an S or a C? C apo S? How do you spell infinitesimal?
Het mesaj Amerika.
Mesaj? Okay. Some noise infinitesimal. Okay, with an S. So it's correct, okay? With I, thanks Christina. So let's assume that we have an infinitesimal small magnetic dipole antenna with a current IM. We call this IM because this is a magnetic dipole. And we assume also that this antenna has a length scale proportional to L, or let's say L, equal to L. And we need to find this magnetic dipole moment. This is pointing along the AZ. Okay, so we preserve that standard orientation, and the question for us is to find these. So we need to find these field components. Now, since we might need some part of the board, allow me to erase this one. And probably okay, so what we do here is that all we need to do is, I suggest you to go to slide 13, and let me check here also. And if you have downloaded this, I found it. Okay. So in slide 13, what is E5? What is the electric field along the? What is it like this? ER, E theta, E5, HR. Let's write it like this. So in slide 13, what is ER? What can you say for ER? Or let's have a look at this. Maybe this is better to look. What is E5? Well, E5 is 0. And ER, it is eta. Can you confirm whether I'm writing this correctly? So ER, it's I0L. I0L over 2 pi r squared. Over 2 pi r squared. Cosine theta. Cosine theta 1 plus 1 over jkr. E to the power minus jkr. E to the power minus jkr. So this is ER, but this is for electric dipole antenna. This is the ER. Now we are asking about the magnetic one. Now the magnetic dipole moment it is going to be we simply have to, and regarding this, actually there is a wonderful table in a textbook where you can see a direct equivalence between the two sets of equations, or which quantities you need to interchange. So one essential part that I always remember is that if here we have the intrinsic impedance, when we write the expression for the HR, we would have the inverse of the intrinsic impedance. So here for HR, we have it's everything the same, but do we have a negative sign? No, apparently we don't. Okay. So this is IM, because this is the current, magnetic current times M, divided by 2 pi. Intrinsic impedance is here, over R squared, cosine theta. So this is the old expression we have for currents, for antennas that we have derived this. This is how we get the HR. Now the next expression we want to find, let's see what we have for the previous case. From slide 13 of last session's equations, we see that we have the expression for E theta. This is E theta. And E theta is equal to J intrinsic impedance KL0I, okay, I0, which is the current, times the length scale of the antenna, and K is equal to 2 pi divided by lambda. That's what the K stands for. Divided, we have sine theta divided by 2 pi r, and then, sorry, this is 4 pi r. Sine theta, we wrote this one, and then we have 3 terms where 2 are real values, 1 is a complex value with a minus, so this is 1 plus 1 over jkr minus 1 over kr squared e to the power minus jkr. So this is the E theta. From E theta, we immediately have to write down the H theta, and H theta would be equal to the JKI, so we have here JKIM, the magnetic current, times the K we did, the current L, sine theta, the intrinsic impedance that appears to be here, it will appear now here, 4 pi and the rest it will be the same. So these terms, they all appear. But let me check, I didn't make any mistake. It's plus 1 over jkr minus kr squared. Okay. 1 minus good. And now we are given also the H phi. H phi. Now when we say given, this was for the electric infinitesimally small electric dipole antenna. This is JKI0L. JK, the current times the length scale divided by 4 pi r. And in fact, these two are strongly coupled together because we have that H phi is equal to A theta divided by intrinsic impedance. There is this, they are directly related with respect to each other, or they are reciprocals of each other. This is for, then we have times 1 plus minus 1 over jkr sine theta e to the power minus jkr, e to the power minus jkr. From here, we can write the A electric field phi, and again, what we get here for the E phi, this will be equal to minus J K I M L divided by 40 pi R, the same curve, sine theta. Okay, so we were given these three expressions, which were for the non-zero terms, and then we had also some zero terms which were equal to zero. In the electric field case, we had the E phi 0. We have also, actually what is left from this, we have HR is equal to 0. And H theta is equal to 0. H theta is equal to 0. Now, in a similar way, we should also determine what is the H phi. This is 0. This is ER. This is 0. And we have E theta is also equal to 0. So on one side, we have the electric dipole. On the other side, we have the magnetic dipole. Okay. Now, when we solve this problem for the antenna which has electric field dipole, we also calculated the directivity. And the directivity that we found, I'm going over the slides now, we found a directivity which was equal to 3 divided by 2. So here, the D, it was equal to 3 divided by 2. And in fact, the same directivity is also equivalent. So this stands for this electric, but this is also the same for the magnetic dipole antenna. So this is also just an example of how we relate the different types of antennas. And with different types of antennas, we simply mean having electric current as a source versus having a magnetic dipole moment as a source. Okay. So let's also consider for a moment, we just want to compare 3 different cases. So whenever we started the analysis of infinitesimally small antennas or line antennas, we always considered the direction as the current was equal to I times AZ, okay? And then we also considered a different case when the antenna, it was oriented along the x-axis. And in this case, we had that the direction of the current or of the dipole is pointing I times AX, okay? And when we had this second case, we did this this example the last time, we needed to figure out what was the dot product between AX with AI. Okay. So we needed to do this because we wanted, so this was, if this is the X, this would be the Y, this would be the Z. We needed to figure this out because we had some angles that we kind of made up, okay? When I say made up, assuming that this is, so we had to make up these angles because the symmetry which is going to be preserved, it depends on the direction of the current, which in some way, I can also represent it like this. So if this is the small dipole, which is this piece of chalk, now the symmetry, it will be such that there is no difference if we are to the left or to the right of this dipole moment, or to the top or the bottom, okay? Now, if the current is pointing in this direction, then the fundamental angle that we have to consider is going to be this, this angle. And the angle which is orthogonal to this, we will have a symmetry with respect to the angle orthogonal to this, okay? In the same way that if we have this small dipole, the symmetry will be that we have a symmetry not with respect to the angle that the angle theta, but is the angle. So this is oriented around the z. This is the angle theta where all the quantities will depend on. Even the expressions that we just solved for the previous example, we noticed a lot of cosine theta, sine theta, which was included in the expressions, and it was this theta. And the symmetry, it was with respect to phi, which means that if we are here versus here or on the back side, we are not noticing anything different, okay, because it was symmetric. So the same story we also do here. And in order to derive the relevant relationships, so let me do it like this. So we have this configuration. Often we see these a lot, cosine theta and sine theta. Now when you come here, all we will care about, it will be cosine psi, sine psi, okay? So it's a different angle, which is measured with respect to the x-axis. Now, let's assume for a moment, we can also have a different configuration where the dipole moment can be pointing in this direction along the y. This would be x, this would be z. In this case, which means that the I would be equal to I0 AY, then the relevant angle here, it would be an angle which extends in this direction, and then the important angle would be this then, right? So we'd have an angle psi here. So the place of cosine theta, sine theta, that we use it as a general reference, is going to be now an angle psi, whose cosine can be immediately be identified if we do the dot product of AY times AR, okay? Now, let's assume, we can also assume another case where, sorry, this is X, and this is Y, and this is Z. So we can have also another case where the current might be pointing by an angle pi over 4 with respect to X, and it is pointing in the, or at least, sorry, it has to be a dipole, and let's denote it like this, okay? So it's just it's on the xy plane with an angle of pi over 4. In this case, we would have to, so it looks like we would have still to figure out, first of all, let's assign a unit vector. So let's call this one A dipole, AD, okay? And then with respect to this AD, we are going to have a, we always are saying this, right? So the symmetry, it will be along this angle, which is orthogonal to this angle psi, right? And now we always need to find these cosines and sines. And now the cosine psi here, it's going to be equal to the unit vector along the dipole times AR, okay? And the dot product AR. Only this AD, in this case, how can we write this one in terms of AX and AY? In order to do this, we may just represent it like this. So the unit vector along the dipole would be equal to AX plus AY, all divided by the square root of 2. Okay, so this would be the AD. And the moment that we want to calculate AD dot product with AR, this means that we would have a constant number here, 1 over 2. Sorry, 1 over square root of 2 times AX plus AY dot product with AR, and then as a result we'll get that this is equal to 1 over square root of 2 AX dot AR plus AUI dot AR again, okay? So in principle it will simply be the summation of whatever term we get here, when the current is pointing along the x-axis, sorry, the dipole, plus the summation of whatever we get the term here, divided by the square root of 1 over 2, because they have normal weight, since the angle with respect to x is pi over 4, and the angle with respect to y is also pi over 4. Now, what is AX dot product with AR? From last time, or we can also derive this now, AX dot AR, we need to this is the angle theta. It will be projected down here at angle phi, and we have to assume that this is the AR, and this AR, it has to first, the projection of AR on the xy plane is going to be equal to sine theta, and then it's going to be some line which is shorter in magnitude than AR, but that one, then we would have to do to find, we have to multiply with the cosine of this angle here, which is phi. So this is going to be cosine phi plus, then AY dot AR, again, we have to project the AR onto xy plane, which is still sine theta, and then we have to multiply by sine phi. So there is a little difference between, and it is also imperative that the dot product between any vector on the oriented by an angle phi with respect to x and with respect to y, we have to use cosine theta. It's not very difficult also. It's good to try to visualize a picture like this, where we can have a unit vector pointing in this direction. Let's call this one AD in this case. This was angle phi. This is how we denoted it. And to find the dot product with AX here, we have to use, so if we do it like, let's do it like this actually. So we have AD dot product with AX, this is equal to cosine phi, right? But meanwhile, the AD dot product with AY, this is going to be equal to cosine alpha, where alpha is this angle here. But we know that cosine alpha is equal to sine phi, comme ne tient tot sues, shumë cilë është e barabartë me të dyta, sinus është e barabartë me cosinusin. So here we can say that this is equal to simply sine phi. So this is why we have the sine phi and here. So this is how we can generate these expressions, and then Wait a second. So we found here what is this is the cosine, yes. And then we need also to find the sine. And the sine so the cosine, sorry, this is we have this expression, and then we would have to write down. And so this is actually we did this. This is almost done. We just need to include so let me now to write the expressions here. Let me try to find in the sine theta. Sine theta. E theta. Yes. So now regarding this, we just need to look at either slide 29 to look for similarities, or slide, yeah, let's have a look at slide 13 again, okay? So we can have also a look at slide 13. We have h phi 4 pi r e to the power k sine theta. Yeah, that's good. So yes, you can have a look at as we said, slide 13. So now everything is done. We just need to substitute this expression for the cosine side and the sine side into the direct expressions of the slide 13, which we can write like this. So over there, we have that, let's write E theta, and let's assume far field. In far field, we have that E theta. Now, I'm not writing this one. I'm not, actually, I wish, well, we erase that one, but E theta is J intrinsic impedance, Ki0, K, the current, I0L, divided by 4 pi r, sine theta. Sine theta 1 plus, so we have these terms here, 1 plus 1 over jkr minus 1 over kr squared times e to the power jkr. Now, in this expression, since we are dealing with the far field, this term converges to 0 because 1 over r, it goes to 0. So what remains, and in fact, let's also say the following. In far field, the term that is preserved, it is this term. It is 1 over r, because we are going to multiply this 1 over r with this one. So it looks like the surviving term is this. This will remain in here. But we have another term, which is 1 over r here times 1 over r here. We have also this other term, which is 1 divided by jkr squared. This term converges to 0 because it becomes small very fast, as it is 1 over r squared. Similarly, we have 1 over r here multiplied by 1 over r squared. So for sure, this term will also diverge pretty soon. So again, let's write here, in theta is equal to j eta k I0L sine theta over 4 pi r e to the power minus jki. Good. Now, what remains for us is that this was actually, what this is, you can find this one on the calculations we have done in the, let me see for a moment, we have also sine theta again, so it looks like we just need to include the sine theta. Okay. And by the way, I'm saying sine theta, it's sine psi. So this sine psi, I may let me use the top of the board. Sine 1 minus cosine squared, so this is going to be equal to 1 minus 1 over 2 sine squared cosine phi squared. No, wait a second. 1 minus 1 over 2 is plus sine sine. So then JT as L. Or pi r sine theta e to the power. Now, we don't need to change much here, we just keep up with I0, L. Okay, so, but in the final expression, we may have to substitute this term in here. So we do all of these change of variables just to try to represent as best as possible the symmetry of the specific orientation. Last session, I think we did the case when so if you go over the class recordings for the previous sessions, we did when the dipole was pointing along the x-axis. This is the case when it is pointing along the x and y and represented by this unit vector as shown here. And then the rest, it will be just, so the only tricky part, it was just getting this term, and then we just get these equations that we have calculated before, and we substitute. And then, in fact, the only thing that we substituted was this sine theta here. We substituted with the sine psi in here. Any question?